Hello everybody and welcome to Chapter 7 on the Central Limit Theorem for sample means. Just a couple of reminders this week. By Monday of week 7, you should have completed quiz 3 and completed the Chapter 6 web-assigned homework. And by Friday of the 7th week, make sure that you've watched the Chapter 7 lecture and completed the Chapter 7 lecture form for attendance purposes. In Chapter 7, the only section that we're going to concentrate on is the central limit theorem as it applies to sample means. There is a central limit as it applies to sample sums, and it's interesting reading and I highly recommend it. However, for the purposes of this discussion, we'll only stick to sample means as it makes our job a little bit easier. So in section 7.1, let's start talking about what it means for the central limit theorem and sample means. When we talk about sampling, one of the things that we're interested in is what would happen if we started looking at samples of size n and comparing the samples. When we were previously dealing with the normal distribution, we were dealing with distribution within a single sample. But now we're interested in looking at what happens if we have multiple samples. What can we say about those multiple sample means? A sampling error is the error that results from using to estimate a population characteristic. If I were to use a sample of 100 heights of male students at New England Tech, and I were to compare that to the mean height of all males in the U.S. population, certainly I'm not going to get the same number. But I can use that sample of the heights of the students, of 100 students, as an estimate. The sampling error would be how far off I am from the actual population characteristic, which is the height of all males. A sampling distribution of the sample mean says that for a variable x of a given size, the distribution of the variable is called the sampling distribution of the sampling mean. So if I were to go through and I were to find a second sample of 100 students from New England Tech, and then a third sample of 100 students from New England Tech, and so on, until I had a lot of samples, I would be interested in the sampling distribution of the mean of each of those samples, and what could we say about it? And one big thing that we say about it right away is due to something called the central limit theorem. And it says this: for a relatively large sample size x, the variable x bar, which is the sample mean, is approximately normally distributed. And regardless of the distribution of the variable under consideration, the approximation becomes better with increasing sample size. So if I had a very small sample of size 5 students, it certainly wouldn't be as good as a sample of size 100 students, or even 1,000 students. So as we get a larger and larger sample size, we're able to get a better and better picture of what the population looks like. Well, this stands to reason. So some terms to know right here, and then we'll illustrate this. Suppose that a variable x of a population has mean mu and a standard deviation sigma. Well then, for samples of size n, the mean x bar equals the population mean, which we'll show. The standard deviation of x bar equals the population of the standard deviation divided by the square root of the sample size. And so sigma of x bar is going to be equal to sigma, the population standard deviation, divided by the square root of n, the sample size. If n is normally distributed, so is x bar, regardless of the sample size. And if the sample size is large, x bar is approximately normally distributed, regardless of the distribution of x. The distribution of the sample means then is approximately normally distributed with a mean of mu x bar, which is equal to the population mean, and sigma divided by the square root of n. So we'll use this fact here shortly. But let's take a look at an example of this at work. And let's say that I have a ridiculously small population of 5 basketball players on a team. So this is the population. Although it's a very small population, probably unrealistic that we would only have a population of size 5. Let's use this as an example of what this central limit theorem means. So in my sample, in my population of 5 basketball players, I'm going to take them 2 at a time. And I'm going to see what the possible heights of each of these size 2 samples are. So I lined up all 10 of my possible samples here. These are all of the possible samples that we can get from a population of size 5, and there's only 10 of those. Here are their heights, 76 and 78 for A and B, 76 and 79, and so on. And here's their mean heights. Well, let's take a look at this. 77, 77.5, 78.5, 81.0, and on down the list. Well, this is useful. What we're going to do is we're going to take a look at this in Excel. And let's just talk about these statistics here. So here's my Excel spreadsheet of my sample heights, 76, 78, average 77. The mean, if I were to take the mean of everything in this column right here, look at all of these means right here. One thing that we find right away is that the mean of all of those sample means will be exactly equal to the population mean. What do I mean? Well, here it is. Let's take our average of the entries in column D here of our table. And there it is. That is the mean. Well, if we went back and we looked at our players and their average height, well, the mean height is in fact 80. There is a standard deviation for these population means, and if we look at all of our possible means and took the average of those, what we would find is that the average deviation of each of these population means away from these sample means away from the population mean of 80, and look at the standard deviation, we call that the standard error. That's the standard deviation of all of our means in our distribution. Okay. So a dot plot for these sampling means is shown right here. Let's make some observations about the sampling error when the mean height of a random sample of 2 players is used to estimate the population mean height. What can we say? Well, this is fairly spread out. We can see that the samples range, the sample means range from 77 to just less than 84. And the probability that for a sample of size 2, the mean will be within 1 inch of the actual population actually looks to be about 3 out of 10. There are 3 samples right here in the interval from 79 to 81 that fit that category, and out of the 10 possible samples, we see that just 3 of them. So we have a 3 out of 10 chance that our sampling error is within 1 inch of the actual population mean. All right, let's try this again. Let's consider a small population again of our basketball players A, B, C, D, and E, their heights in inches here. This time let's take our samples 3 at a time, and there's 10 of those. And I've found the mean of each of these samples. Well, what observations can we make about that? Let's go back to Excel. Check it out here. So I'm going to get my mean right here. If you were to do this as an exercise yourself, you might see this. Equals average. Let's get our average. Here it is. And our heights right there, that's our sample set. There it is, and this is our mean. And so now we're going to just copy that all the way down here as a formula. All right, here are each of our mean heights as shown in our table. Right, there they are. Okay, so what could we say about these things? Well, of course, the mean of these sample means is the same as the population mean. Once again, if I get the average of all the entries here in column E, which is where my mean is now, sure enough, the average is 80. And again, if I were to work out my standard error right here, let's see what happens. What I'm going to do is I'm going to take the difference between my sample mean and my population mean squared, and I'm going to do that for each of these rows here. Find the column. The standard error, which is the standard deviation of that column right there, is a little bit smaller this time. All right, so let's take a look back at this here in our table. What else can we say? Well, let's compare what happened when we had a sample of size 2 and a sample of size 1. We can see that the spread of our data is much closer together this time, right? Just like we said we had a smaller average standard deviation for each of these means as compared to the samples of size 2, we can see that as our sample size increased, our standard deviation, our standard error, decreased. What's more, if we were interested in finding the probability that for a random sample of size 3, the sampling error will be within 1 inch or less of the population mean, we see that we now have 1, 2, 3, 4, 5 out of the 10 samples within that 1 inch range. If we continue to increase the sample size, here's our sample of size 3 here in the row, and we go to a sample of size 4, we see that all of our samples would be very close. And of course, the sample of size 5, that's our entire population. That's the census right there. The average is 80. Well, clearly, as the sample size increases and gets closer to the population size, it appears as though our standard error goes down. Our standard deviation decreases. And that's what we want to know about this one.